In this problem, we're told approximately what magnitude force, Fm, must the extensor muscle in the upper arm exert on the lower arm to hold a 7.3 kilogram shot put in this figure. Assume the lower arm has a mass of 2.3 kilograms and its center of gravity is 12 centimeters from the elbow joint pivot. So this is the diagram in the book. And so essentially this right here is going to be where we're rotating around. This is the elbow joint. We have this force Fm, right? So this is our force Fm. And so we know it's 2.5 centimeters away. We have this ball in this hand, right? A shot put. We know it's 7.3 kilograms and it's 30 centimeters away from this point right here. They also tell us though that the lower arm is going to have a mass of 2.3 kilograms. So this right here is our lower arm, right? This is our arm. And we know it's going to have a mass of 2.3 kilograms and its center of gravity is 12 centimeters from the elbow joint. So from the elbow joint to the center of gravity, I'm just going to say here, it's probably not perfectly to scale, but doesn't really matter. This distance right here is going to be 12 centimeters. And so let's write down the given. So what are we given? We're given the mass of, our shot put. I'm just going to write ms. So the mass of the shot put is 7.3 kilograms. The mass of our arm, they tell us too. They tell us it's 2.3 kilograms. So I'm just going to call it MA, mass of the arm, is 2.3 kilograms. Cool. So how do we solve these problems? So the way you want to solve these problems is by finding the sum of the torque. And you'll see why in a second. But essentially, we're finding the sum of the torque. So how do we go about doing this? So you need to know that torque equals RF times the sine of theta, right? You should know this, radius times force times the sine of theta. And so essentially what we're rotating around in this point is the elbow joint. So you can imagine it like this, even though the arm can't do that, but it rotates like this up and down. So imagine we're rotating around this point. So the distance from where the force is being applied to this rotational point is our radius, right? And we have forces. Well, we have them, but we don't know them yet exactly, but we'll do that. And then the sine of theta, you don't have to worry about the sine of theta when you're doing perpendicular angles. So in this case, all of our forces are going to be perpendicular. So I'm not going to include the sine of theta in our calculations, but just know that the forces are being applied to this are going to be perpendicular to the radius, meaning that this is going to be 90 and the sine of 90 is just 1. So really, in this problem, it's just going to be RF. And so what you can call it is distance, DF, or it's RF, whatever you want to call it, but essentially just the distance between the forces being applied to your rotational point, which in this case is the elbow joint. So just keep that in mind. And so what we want to do is add up all the different torques, and that's going to allow us to solve for FM. But what we want to do first is just label or draw a free body diagram of what's going on here. So this is our drawing, but let's draw the forces acting on it because the forces are going to be this sum of the torque, right? Because we need them because it's RF, right? That's the formula for torque. But yeah, so let's draw the free body diagram next. So you can draw this many ways. I'm just going to go draw it like this. So imagine this right here is our arm. So this is our arm right here. We know the elbow joint is, let's say it's right here. So what are the different forces acting? They tell us we have Fm, right? This is a force acting right here. And we know its distance from this is going to be 2.5 centimeters. So let's write that in. So this right here is 2.5 centimeters. That's cool. And then we also have, let's do this one next. So this ball is going to have the force of gravity acting on it, right? Which is just mg, right? So we have another force right here, mg. So let me draw it like this. So mg, this is going to be the force as a result of the shot put. It's going to be weighing down on us, right? And so the distance from this point we know is going to be 30 centimeters, right? They tell us, labeled in right here, 30 centimeters. So let's draw that now. So 30 centimeters. And then what other force do we have? So when they tell you the mass of our arm, since it has a mass, it's going to have force or like a force due to gravity. So it's going to have a force acting down this way. So this isn't to scale perfectly, but this is mg, right? And this is as a result of the arm, right? So this is the ball, this is the arm. So it's going to have gravity pulling down on it essentially. And we know it's 12 centimeters away. So the distance here is 12 centimeters. So yeah, these are gonna be all the forces, and then the radius or the distance between the force and the center, right? So now we've got that. What we can do is just add them all up. But keep in mind you have to note the direction it's going in. So when we talk about rotational, right, things that are rotating, you generally say the counterclockwise direction is negative. So if it makes it travel this way, right, this way I'm going, imagine like a clock, we label it or sorry, counterclockwise is positive. Sorry, I mixed that up. So counterclockwise we label as positive. So if it goes in this direction, the direction I'm going in right now, we are going to call that positive, right? Going backwards on a clock. But if it goes this way on a clock, counterclockwise, we call it negative. So just keep that in mind, and you'll see how it works in this situation. But let's start with this force. So Fm, right? Torque equals force times radius. So these are all radii, right? So the force here is just Fm. We don't know it. That's what we're solving for. Keep in mind the direction this is also going in, though. So it's going to cause it to rotate this way, right? When we push down this way, it causes it to rotate this way, right? Because imagine it's going like this. And so what direction is this? This is going to be counterclockwise. Therefore, it's positive. So counterclockwise is positive. So that's that. And then we don't need to make it negative since it's positive. And then the distance is 2.5 centimeters. And so we know 2.5, right? 2.5 is just going to be, right? We need it in meters. This needs to be in meters, or the distance needs to be in meters. And then the force has to be in newtons, right? So, or yeah, essentially it needs to be in newtons. So this right here is going to be 0.025 meters, right? Just divided by 100. You should know how to do that by now. So 0.025 meters, that's going to be the distance or the radius. Now let's move on to the next force. So let's do this one now. Is this going to cause it to go in the counterclockwise or clockwise direction? So think about how it works. It's going to be pushing down this way, so it'll go this way. And what direction is this? This is going to be clockwise, therefore it's negative. So make sure you label this one negative. So minus the force, which we know is going to be just m times g. Yeah, but where is this at? This is the mass of the arm, correct? So we want to label it as A, right? Mass of the arm. So it's 2.3. So minus 2.3. Or let's write the force first. So the force is just, oh yeah, we are writing the force. 2.3, right? Times g, which is 9.8. And then we multiply by the distance. And how far away is it? So we know it's going to be 12 centimeters away from the rotational point, right? RF. This is the force. The radius is going to be 12 centimeters, which is just 0.12 meters, right? So that's going to be the distance away from that. So that's this force. Now let's do the next one. I'm going to move down right here. So minus the force is going to be mg once again. The mass is going to be 7.3, right? Because this is the shot put now, right? It's corresponding to the place on the graph. So 7.3 times 9.8. And then multiply it by the distance, and the distance is 30 centimeters. So just 0.3. So now we've got it like this. Actually no. So what we want to do is solve for Fm. And keep in mind, the total torque has to equal to 0. Why is that? So it's equal to 0 because it's not moving. So since this equals to 0, this whole thing, since it's stabilized, we can just solve for Fm. So this is 0. So what we want to do is solve for Fm. So we can move both of these to the other side. And if you do that, you're going to get Fm times 0.025 is equal to, and then both of these are going to become positive and add them together. So 2.3 times 9.8 times 0.12 plus 7.3 times 9.8 times 0.3. And then all that is going to be over, right? Because we want to divide by 0.025. So go ahead and do that. 0.025. Cool. So now if we go ahead and solve for Fm, just plug these in your calculator. I'll do it here too. So 2.3 times 9.8 times 0.12 plus 7.3 times 9.8 times 0.3. And then go ahead and divide that by 0.025. So if you go ahead and do that, you're going to get Fm equals 966.672. So keep in mind this is in newtons, right? Because we're doing a force. So 966.672 newtons. I'm going to round to 970. You can round however your teacher wants you to, but I'm just rounding to the tens place. So 970 newtons. But yeah, so this right here is going to be this Fm. All we did was added the torque, and that's going to allow us to solve for Fm. But yeah, so this right here is going to be the magnitude of force Fm. So 970 newtons. Yeah, hopefully you found this video useful.